All right. So here's what we started yesterday. We started talking about, more specifically, about some properties of functions and analyzing the graphs of functions. And we said you can tell by looking at a graph whether or not it came from a function because it's got to pass the vertical line test. Okay, so we had an example here where I can erase a couple of these. Okay, that passes the vertical line test. This one doesn't, and this one doesn't in this one little space, but that's enough to make it so that it's not a function. Then we also went through and we were talking about how to find the domain of a function by looking at the equation. So here's a function right here. The only number that we can't plug into this is 6 because that creates a domain issue like we've been talking about. If you have division, even roots, or logarithms, you've got to be a little bit careful with this. So the number we can't plug in here is a 6. If we're doing a radical, we've got to make sure that we're taking the square root of a positive, or at the very least 0. So we set that expression, that radicand greater than or equal to 0, and then we solve that, and that would be the domain. And then we said the easiest way to find the domain, and the range for that matter, is if you've got a graph. And we use what we'll call the squish technique. If I want to find the domain, I take the graph and I squish it onto the x-axis. So everything from here all the way to here is covered. And notice that's an open endpoint, so we didn't include the -2. And then if we squish it on the y-axis, everything from here all the way up to there is covered. And we talked about why that's a square bracket on both of those. Okay? And that's where we left off. All right? Now, let's talk about what the zeros of a function are. Okay? Because this topic is used over and over and over again. It's amazing how many places this comes up. Okay? If we're discussing the zeros of a function, what we're talking about is where the where the graph crosses the x-axis. And the reason we call it a zero of the function is because the y-coordinate on the x-axis, any point on the x-axis, you didn't go up or down, so that means the y-coordinate is 0. Okay, so that's why we call it a 0. So when we're trying to find x-intercepts, what we're trying to find is where does the function equal 0? We literally set the function equal to 0. And there are a couple other vocabulary words that we ought to be familiar with, and maybe you use these in another class. We call them zeros, we call them roots, we call them solutions, and we call them x-intercepts. Okay? So if you've heard that terminology before, then that's great. So on this problem right here, or each one of these, what we want to do is we want to find the zeros. In other words, we want to find where it equals 0. So we're going to set this equal to 0. And does that look familiar? And how would we solve it? It's the math F word. What are we going to do? We're going to factor. Okay? Factoring isn't the funnest thing in the world, but it doesn't go away. It's something we need to be really good at. Multiply to be +4, combine to be -5. What's going to do that? Okay. -4 and -1. And so what's the 0 that comes from this factor? +4. And what's the 0 that comes from this one? +1. So our two zeros are 4 and 1. Okay? Those are the zeros. Again, they're called zeros because if you plug them in, what does the function equal? It equals 0. So if we look at one like this, now this is kind of interesting, and if you've seen this before, that's great. If you haven't, I really want you to pay attention because this is going to come up again in this class as well as when you take Math 1050. We want to know when this equals 0. Now, that is a rational expression. Working with fractional expressions isn't the funnest thing in the world, but here's something really cool about this one here. What's the only part of a fraction that can make the whole thing equal to 0? Just the... Okay, I'm hearing zeros, I'm hearing numerator, I'm hearing denominator. It's the numerator, okay? The only thing that can make a fraction equal to 0 is the numerator. So even though we've got this ugly expression here, set equal to 0, the only part of this that I need to worry about is the numerator. And think about it. If I had 0 over 4, what's the answer? Answer's 0. What if I had 4 over 0? What's the answer? Undefined. Okay? We want it to be equal to 0. It doesn't matter what the bottom is. As long as the bottom's a number other than 0, we're okay. So on this problem right here, we basically get to ignore the denominator. We don't have to worry about that. All we're interested in is when is 5x plus 4 equal to 0? So we could do this the quick way, or we could move that over, that's a -4, then divide by 5. The other way to think of it is, and we talked about this in chapter P, it's opposite of the 4, divide by 5, that's the 0. Okay, that's what would make that function equal to 0. Okay? Any questions there? Okay, let's take a look at the next one. What would make this equal to 0? Any ideas? Well, you literally set it equal to 0, right? So I'm going to take the square root of x squared minus 5 and set it equal to 0. I want to get the x by itself, but right now it's underneath the radical. It's underneath the square root. So what am I going to do? I'm going to square both sides. Now the interesting thing about this one is, if I square this side, I get x squared minus 5. If I square this side, I still get 0. The only way that radical is going to be 0 is if the radicand, the stuff underneath, is 0. Okay? Now let's finish solving this. Any ideas on this? How do I solve x squared minus 5 equals 0? Sven? Yeah, let's add 5 to both sides. Let's isolate the square. So I'm going to add 5 to both sides. And then how do I get rid of the squaring? Take the square root of both sides. So I get x equals, and I'm going to write radical 5 here. Is that the answer? It's not. Logan, what do we need? We need a plus or minus, because when we put the square root in the problem, we have to account for the fact that we don't know whether it was positive or negative to begin with. Okay? Very good. Any questions? Okay. So we're going to go back really quickly, and we're going to review some symmetry that we talked about before. We talked about symmetry with the y-axis, and this is what we found. So here was the example that we used. We used a regular old parabola. It looked like this. We said that was symmetric with the y-axis because it doesn't matter whether you go to the right or the left. Like this point right here is 2, 4. This point is -2, 4. So the way we pointed this out is if xy is on the graph, so is -xy. So if you go to the right or the left, it doesn't matter. You get the exact same y value. You get the exact same function value. So if we were to put this in function notation, what it means is if you plug in a -x, you get the exact same as if you plugged in a positive x. So going to the left gives you the same thing as if you were going to the right. So if we shorten this, f of -x is the same as f of x. Okay, so that's what we talked about with symmetry with the y-axis, fold symmetry. Okay, well these types of functions come up so often, these functions that are symmetric with the y-axis, we give them a name. Does anybody remember what they're called, or has anybody seen these before? Noah? Okay, this is a parabola, yep. Okay, we call this an even function. Okay, if it's symmetric with the y-axis, we'll just say even. Okay, remember mathematicians tend to be a little bit on the lazy side. Okay, they like to shorten things and make them a little more concise. So rather than on every single graph that's symmetric with the y-axis, that's a lot of words. We just use the word even to describe that. Okay, and there's a good reason for that that we can talk about when we study this a little bit more in depth. Okay, then there's another type of symmetry that we're interested in. It's symmetry with the origin. Okay, and if we call this even, guess what we call this? We're going to call this odd. Okay, and here's what odd looks like. Remember, symmetric with the y-axis, or excuse me, symmetric with the origin means that if you spin this graph around the origin, put your pencil on the origin and turn it 180 degrees, the graph looks exactly the same. And when we graphed this before, one of the points that we graphed was 2, 8. This corresponding point over here was -2, -8. So again, we're comparing what happens when we go to the left and the right. When we go to the right, we get 8. When we go to the left, we get -8. So this is 2, 8. This is -2, 8. And we made the point that if it's symmetric with the origin, if xy is on the graph, what else is on the graph? Negative x, negative y. They both change signs, right? So what this means is f of negative x, if you plug in a negative x, you get the exact opposite of what you get when you plug in a positive x, or vice versa. So this means you get the exact opposite. And remember, the word opposite means negative. So if I plug in a negative x, I get the negative of what I get when I plug in a positive x. Okay? Any questions there? Okay, let's look at the next page then. Okay? We did talk about one other type of symmetry. We talked about symmetry with the x-axis. Does anybody remember why we don't really use that very much? Why do we not care about symmetry with the x-axis? Tammy? Because it's not a function. Okay? It wouldn't be a function. Okay? Let's take a quick look at what would happen here. If I had something that was symmetric with the x-axis, something like this right here, it wouldn't pass the vertical line test. Okay? So that's why we don't, there is a usefulness for that, but not when we're dealing with functions. Okay? So it's pretty easy to tell by looking at a graph whether or not it's odd or even. Remember, odd means symmetric with the origin. Okay? Point symmetry, rotational symmetry around the origin. Even means symmetric with the y-axis. The right looks the same as the left. It's one thing to tell by looking at it. It's another to be able to just grab a function and be able to tell which it is. Okay? So we've got this little test for whether or not we've got an odd function or an even function. And the cool part is they start out exactly the same. You do exactly the same thing for both parts of this test. You replace every x with a negative x. Notice that it's in parentheses. And then you simplify. It's the same for both of these. If you get the exact same thing as the original equation, then it's got to be even. If you get the exact opposite, an opposite would mean it has a negative in front of the whole thing, essentially, then we'd say that it's odd. So let's take a look at this problem right here. Okay, the test for both of these starts the same, doesn't it, Hop? What do I do here on this one? No. Say plug in a negative x. We're going to plug in a negative x. Thank you very much. So if I plug in a negative x, and I'm going to put that in parentheses, then I simplify. How many negatives do I have right here? 4. So is the answer positive or negative? Positive. So this is x to the 4th. Okay. How many negatives altogether do I have in this second term here? Altogether? 1 out front, 2 here, so that's going to be 3 altogether. So is the answer negative or positive? Negative. So this is negative 4x squared. So then I take a look at this. That's the simplified version now, and I compare it with the original. Is it exactly the same? If it's exactly the same, then it's even. Okay? It's that simple. You plug in a negative x, you simplify. If it's the exact same, it's even. If it's the exact opposite, it's odd. What if it's neither of those? What if it's not quite the same and not quite the exact opposite? Yeah. There's no symmetry, and we say that it would be neither. Okay? It doesn't have any symmetry. Okay? So let's take a look at the next one. Again, the test starts exactly the same. You're going to plug in a negative x in parentheses. 3 negatives, that makes it a negative 2x cubed. 1 negative, that makes it a negative x. Compare that to the original one. Is it the exact same? No way, so it's not even. Is it the exact opposite? It is the exact opposite, and let me show you something that on this one seems a little bit silly, but in the long run you're going to be better off. When we say it's the exact opposite, it means you can pull out a negative. What would happen if I pulled out a negative? 2x cubed plus x, right? Okay, compare this with the original one. Put that in parentheses. Is that stuff in parentheses exactly the same? Yep, it's just got a negative in front, so the whole thing is indeed the opposite. Okay, so that means this one is odd. You with me there? Okay, let's look at the next one, and then they're going to get kind of interesting after that. If I plug in a negative x and simplify, I get negative x cubed minus 1. And let's compare that with the original one. Is there any way it's exactly the same? No. So there's no way it's even. Is it the exact opposite? It's not. Okay? So this one isn't odd and it isn't even. So this one is neither. Again, let me show you another way that you can tell. If I take out the negative, I'd get x cubed plus 1. There's the negative out front, meaning opposite, and look what's here. Is that exactly the same? It's not. Okay? So this one is neither. Okay? There's no symmetry for that one. Okay? All right. This gets a little bit interesting because you've really got to think about this. Square root function. Anybody know what that looks like? Have we seen that before in this class? Looks like this, right? Is there any symmetry to that? No. So this one is going to be neither. Let's try and confirm that using this little test. Plug in a negative x. Is it exactly the same? Nope. Is it the exact opposite? Is it the same as if I just multiplied that by a negative? Nope. Okay, that's why it's neither. Okay, and then we get to the interesting one. So let's take a look at these. Both of these are rational expressions. So the test starts the same way. I'm going to plug in a negative x. Negative x squared plus 9, and then 3 times negative x. This is x squared plus 9, and on the bottom, what do I get? Negative 3x. Is that exactly the same? Nope. Is it the exact opposite? Okay. How many say no, this isn't the exact opposite? How many say yes, this is the exact opposite? Okay. A couple of you? Very good. Okay. Unfortunately, the minority is correct. There were 3 people that got this right. This is the exact opposite. Okay. And to just demonstrate that, will you flip over, look at the front page. I asked you this question. What's the opposite of 3/4? Negative 3/4. If I wrote it this way, isn't that the opposite of 3/4? Where's the negative or the opposite part on this one? Where did they put the negative? It's on the bottom. Okay? So if I were to pull this out front and write x squared plus 9 over 3x, that's the same thing, right? I'm putting it out front. Is it the exact opposite? Yes, it is. So this one is odd. Make sense? With rational expressions, with rational functions, you've got to be a little bit careful. So let's take a look at this one. Let's see if we can do this without, actually showing the work. What happens if I plug in a negative here? I've got 5 negatives and a negative out front. What does the top turn into? Positive x to the 5th. Now, you would need to write this work. You would need to show that it does this. What happens if I plug in a negative here? 3 negatives, so that's going to be negative x cubed plus 1. Exact same? It's not the exact same. There's no way it's the exact same. If you're thinking, well, I could just slide this up on the top, somebody tell me why I can't slide that 1 up on the top. Hot. It's a term. Very good. Okay. If I were to try and do that, here's what I'd have to do. I'd have to do x to the 5th, take out a negative, and this is why that factoring is so important. Okay, that's what I'd have. Then I could slide it on top. Okay, so then I could write it like this. Negative x to the 5th, and the bottom would be x cubed minus 1. Okay, so is it the exact same? Nope. Is it the exact opposite? Nope. Okay, so this is neither. Okay, they can get a little bit tricky. Any questions about that? Okay, We're now going to look at just some definitions and some vocabulary. You may have seen this before. There's not a lot of writing that you need to do here. What I'd like to do on this right here is just look at this. This is a very wordy mathematical definition. So if we were reading the textbook for this section, you'd find a description and a mathematical definition for this that would look very similar to this. Okay? They're not the funnest things to read. Let's read this and let's figure out what it's talking about. It says a function f is increasing, so here's our vocabulary term, increasing, on an interval if for any x1 and x2, so for any two different x's, okay, on the interval where x1 is less than x2. So that means this is on the left and this is on the right. x1 is smaller than x2. So we're going from a small value on the x-axis to a big value on the x-axis. It means that f of x1, this y value is smaller and this one is bigger. So let's think about what that means. I'm going to make some space here. Okay? So what it means is, I'm on the x-axis. Let's say this is x1 and this is x2. So I'm going from left to right. This function value is smaller than this function value. So to go from here to here, I've got to go up. Does that sound like a good way to say increasing? That's all increasing means. What this ugly definition here means is, as you're going from left to right, the function values go up. So increasing means the function goes up from left to right. Now we could take the time to read both of these. Decreasing, guess what decreasing means? It goes down from left to right. Okay? And what about constant? If something's constant, does it change? Doesn't change at all. So it means the graph stays constant from left to right. Now, if it stays constant, it never changes. So if this is our axis, it does this. Goes like that. Doesn't go up, doesn't go down. What is that? Horizontal line. Okay? Horizontal line. Okay? So, some more vocabulary that you've probably heard before. Maximum and minimum. Okay? Maximum is the largest or the greatest function value on an interval, and the idea that it's on an interval is important. And minimum is the smallest or least. Okay? And then this particular textbook uses an additional vocabulary when we're talking about maxes and mins. Okay? So it uses the word relative. Okay? So if we're talking about the relative max or the relative mean, it means either the highest or lowest function value, okay, greatest or smallest, however you want to think of it, okay. Let's see, compared to the points around it. And sometimes we'll say on a little neighborhood. So in a little neighborhood, is it the biggest or the smallest function value? Okay? And then we've got some pictures here. So this right here, on this interval from, everybody watch please. Let me make this a little bit larger. Okay, on the interval from -2 to 0, it's decreasing. On the interval from 0 to 2, it's constant. And on the interval from 2 to 4, it's increasing. Okay? And we normally locate where these things are happening according to the x-coordinates. So we say, where is it increasing? We're asking about where on the x-axis is it increasing. Don't say it's increasing, everybody listen. Don't say it's increasing from 1 to 4. You want to say it's increasing on the interval from 2 to 4. It's decreasing on the interval from -2 to 0. Okay? If we take a look at this one right here, okay, this is the highest point on this little area. So this would be a relative maximum, okay, and this is a relative minimum. And then we've got this other word. It's called absolute max or min. And when we talk about an absolute max or min, what we're talking about is that point is either absolutely the highest or the lowest, largest, smallest, however you want to talk about it, okay, for all the points in the domain, every single one of them. So again, what we've got here is we've got a relative minimum here and a relative minimum here and a relative maximum here. This graph may continue off in other directions, so we won't talk about absolutes on this one. Let's take a look at this one right here. And let's figure out what we've got on this one. Do we have absolute maxes, absolute mins, relative maxes, relative mins? Okay. So does everybody agree that this point right here is the largest function value for this entire function as it's defined? That's the biggest one. Okay. So we would have an absolute max of 4, and it would occur at x equals 2. The maximum function value is the y value. Where it occurs is the x value. Okay? And if you get used to that in this class, it's going to make your stuff in 1050 and 1060 and calculus a lot easier. Okay? This one right here. Okay? This is a minimum, right? Is it an absolute minimum or just a relative minimum? This one is absolute. Okay? Absolute min. What's the minimum function value? What's the smallest function value? -5. So the minimum function value is -5. And where does it occur? At x equals -1. Okay? -1 is where it occurs. -5 is the actual minimum function value. Okay? And notice the other things that they've got on here, just as review. The domain goes from -1 to +4. Would it include +4? Nope. And the range goes from -5 all the way up to +4. Would it include -5? Yep. Would it include +4? Yep. Okay, let's talk about that one right there. Is that, well, it's not a max, is it? There's no way that's a max. Is it a minimum? Relative minimum? Okay. No min. No min or max there. Here's why. Well, can somebody tell me why there's no min there? Raymond. We could have a couple. We can only have one absolute and one absolute max and one absolute min. Okay? But we can have a whole bunch. Like if we look over here, there's a couple relative minimums and there's a couple relative maximums. Alexis, why do we have no minimum there? Very good. It's not filled in. Okay? We can't have a minimum there if it doesn't actually have a point there. Okay? And then you could make the argument, well, what if I chose 0.001 as the minimum? Well, then your neighbor would say, well, I'm going to choose 0.000001. Okay? And then you could argue back and forth and then get in a fight and all that sort of stuff. Okay? If there's no point there, we can't have a minimum. All right? So we want to notice a couple important things about these definitions. Okay? And this is really important. People mess this up all the time because they misconstrue the idea. Increasing and decreasing and constant can only be used to describe a function on an interval. Because of the way the definitions are, you have to be moving from left to right. If you don't go anywhere, if you don't have an interval, if you're just at one particular point, you can't describe it as increasing or decreasing. Okay? Okay, and then we already emphasized this, but just to re-emphasize, when a question asks what is the maximum or minimum value, it's asking for the y coordinate. What is the maximum value? What is the minimum value? Okay, what's the highest and lowest point? Okay, that's a y value. If it says where does it occur, then it's asking for an x coordinate. Just like if we say where is it increasing, we're asking for an interval on the x-axis where it's increasing. Okay? All right. So go ahead and flip the page over. Let's take a look at example number 6. And we just want to make sure that we can apply these definitions and get these right. So take a good look at this. It's a graph. We don't know what function produced this graph. But then it says, what's the domain and what's the range? So we'll use what technique again? Okay, we're going to write it in interval notation, but how are we going to find the domain? Squish it onto the x-axis. This continues going up here and up and out here. So if I squish this down here, the entire x-axis would be covered. So we'd start getting answers at negative infinity and go to positive infinity. That's the domain. Notice how we're going alphabetically. And then let's do the range. If the domain are the x's, the range are the y's, squish this onto the y-axis. Do I have any answers down here? Nope. So where does the range start? Starts at 0 and goes to infinity. Round or square around the 0? Square, very good, because it actually touches 0. This point right here is 3, 0. Okay? Look at the question here. Where? Where is this happening? Where is this increasing? That is a question about the x-coordinates. Okay? So I'm going to grab my highlighter here. Okay? What's it doing here? Increasing or decreasing? Decreasing. Okay? What about from here to here? Okay, so from here to here, and then again from here to here. Please don't say this. Don't say that it's increasing from 1 up to 2. Whoops. 1 up to 2. Okay? That's not where it's increasing. Those are the function values that it changes between, but those are not where it's increasing. So it's increasing from negative, let's see, that's negative 1, isn't it? Negative 1 to 1. And then it increases again from 3 to infinity. Round or square here? It doesn't matter. Most people prefer to put round. If you want to put square, that's fine. We could get in an argument about that. It doesn't matter. Okay? So if that's where it's increasing, where is it decreasing? All the way from here to here, and then again from here to here. Again, where is a question about the x-axis? Where is it decreasing? From negative infinity all the way till we get to 1. And then it starts up again at 1 and goes to positive 3. And again, we're going to do round ones here. What's that? Oh, negative 1. Thank you. Thank you. Okay. Are there any questions as to why those are the answers? Okay. Let me just show you really quick why some people would be bugged about this. What if I did a square bracket around this one and a square bracket around that one? Some people are bothered by the fact that you're saying that it's increasing at 3 and it's also decreasing at 3. Okay? It's not that big a deal because at a particular point it doesn't matter. Increasing and decreasing only matters on intervals. Okay, so it's not that big a deal, but we'll use round brackets there. Okay? And where is this function constant? Nowhere. Nowhere. Okay? All right. So, more applying vocabulary. Is there a local maximum? Or are there more local maximums? Or are there a couple of them? Any local maxes? Yes or no? I see some shaking heads, yes. I see a couple no's. Yes, there is. Remember, a local max is where it kind of has a little peak right here. So it says, what is the local maximum? The local maximum is right here. It's 2. Where does it occur? At x equals 1. Remember, what the maximum is a y value. Where it occurs is an x value. Okay? You'll also see this word occasionally. Instead of somebody saying the absolute maximum, they'll say the global maximum. Okay? So instead of just a local area, we're talking about everywhere. Okay? So local is just kind of in a local little area instead of using the word relative. Okay? Global is like absolute. Okay? So if you see those different types of vocabulary, you'll know what they mean. So is there an absolute global maximum? Nope, because it continues going up. Okay, so the answer there is no. Is there a local minimum or minimums? Okay. This is the smallest point in this little area, and that's the smallest point in this little area. Okay? So technically, these both qualify as local minimums. Okay? One of them is 1, and it occurs at -1, and the other one is 0, and it occurs at 3. Now, what's the best way to describe this particular one right here? Absolute minimum, okay? Or here we'd call it a global minimum. Again, global would be the same as absolute. So the answer there is yes. The global minimum, the smallest point, period, is 0. And where does it occur? At x equals 3. Remember, all of these are y coordinates. What the values are y coordinates. Where they occur are x coordinates. Okay? Any questions? Okay. You've got some problems on your assignment that look like this. It says, find the linear function for which f of -1 is -2 and f of 3 is -4. And my contention would be, my argument would be, you should know how to do this. This just looks weird. Okay? Lynn is shaking her head. Do you know how to do this? Do you know how to do this? Lynn thinks she knows how to do this. Well, how do you think you do this? Excellent. Okay, again, like we said yesterday, the cool thing about function notation is this is telling you that's the x-coordinate and that's the y-coordinate. So it's saying come up with a line that goes through -1, -2. And what's this point right here? 3, -4, right? So what two things do you need to write the equation of a line, Sarah? Two things you need to write the equation of a line. You're going to need a y. You could use x and y intercepts if you had them. Okay? Those happen to be two particular points. Okay? Got to lock this away. If you're going to find the equation of a line, you need two things. Tony, what are they? Okay, you need a point and you need a slope. Do we have a point? Yeah, we've got two of them to choose from. Do we have a slope? We don't have a slope, but do we have enough information we can figure it out? Yeah, we're going to call this one x1, y1, and we're going to call this one x2, y2, and then we're going to use this formula right here, y2 minus y1, x2 minus x1, and so forth. So that problem looks unfamiliar, but do you know how to do it now? This is the stuff we did in 1.2, okay? Any questions? Okay. You don't need to finish that unless you're not quite sure how to do it. I'm not going to take the time to finish that in class. If you've got a question, we'll take a look at it after. Okay, this is a piecewise function. So we're going to graph this piecewise function. How many pieces does it have? Has 3 pieces. Okay. Do you know what this looks like? If I said f of x equals x, or if I said y equals x, I mean, we know what that looks like, right? Okay? It's this line right here. Correct? Where does it look like this line? When x is less than 3. So I'm going to draw a line right here at less than -3. I'm going to draw a line right here. And x is less than 3. Is that the left side or the right side? Left side. So here's what I'm going to do. I'm going to erase all of this, and it looks like that. That's just this piece. Open or close circle at the end point? Open. That's the first piece. I'm going to change colors. Do you know what this looks like? You should. It's a, what is it? Horizontal line. It's a constant function. Okay? It just stays like this all the time. It's always 2. Where does it look like that line? When x is greater than or equal to -3 or less than or equal to -1. So it doesn't look like that everywhere. It only looks like that between -3 and -1. So I'm going to erase everything that's not in that little interval. And I'm going to draw this little line segment right here. What type of endpoints? Open or closed endpoints? Closed endpoints. Okay? So there I've got 2 pieces. Okay, everybody watch. Got those? Watch. Why can't it be this? Why is there no way I could have it look like this? What's that? Well, if this went up, it would intersect. Okay? I'm looking for something else, though. This is a function. Does this pass the vertical line test right here? It doesn't. Okay? So there's no way it could be on top of this piece right here. Okay? And I'll change colors one more time. What does that look like? Crosses at -1, has a slope of 2, right? Okay? It would be this line right here. Why is there no way I could keep all of that? Why can't I keep all of this stuff right here? Hop? Wouldn't pass the vertical line test. Okay? So where does it look like this? When x is greater than 0. So we're going to start right here, and we're going to keep everything over on this side right here. I'm going to erase everything else. Open or closed? Open. Does it matter that there's a little gap in here? That we don't have any points from -1 to 0? Nope, doesn't matter. Okay, that's how they defined the function. That's it. Okay? Any questions? Okay. Noah, does that answer most of your questions that you sent me? Okay. If not, we'll do those tomorrow. Tomorrow you need to make sure that you bring a calculator. I'm going to finish this one up right here. In fact, I may record a very short video and send it to you that you can watch that just explains how to do those. That way we can start just with the calculator problems tomorrow, okay? 1.3 up here. Make sure you bring a calculator tomorrow. Thanks.